Professor Yadav, this year, this BRSI international conference will be held in Trivandrum. You know it.
I don't know, quite honestly.
Yeah,
no.
okay, it was announced.
The date?
It is November 26 to 29. And you would be expected to, as a winner of honor, you will be give a lecture. Yes. Yeah.
So 26 to 29th November, right?
Yes, at Trivandrum. Namaste, Professor Sopori.
Yeah, okay. He will also be there, right? Okay.
Good morning, everybody.
Good morning, good morning.
Good morning, Professor Yadav.
Good morning, how are you?
I'm fine, I'm all right.
So November 26 to 29th, you said, right?
Right.
Which is Sunday. It starts on a Sunday. Okay.
Sunday. Alok, you'll also have to note down these dates.
I've already done that, sir.
Okay, thank you. All the award winners, normally we request them to deliver a talk in the next conference.
We have 5 minutes now. I think we still have 5 minutes.
Good morning, Datta Saab. Good morning, Datta Saab.
Good morning, sir. Good morning. How are you?
I am good. Yeah, thank you. कैसे हैं आप?
बस सर बढ़िया सर. आप कैसे हो सर? अभी आप कहाँ, फ्रांस में हो इंडिया में हो?
अभी फ्रांस में हैं. हाँ.
अच्छा, फ्रांस में. So when are you returning?
4 को पहुंचूंगा दिल्ली, 5 को लखनऊ.
ठीक है सर.
Good morning, everybody.
Good morning. Good morning. Good morning, madam. What a pleasant thing. How are you, madam?
I'm doing well. I hope everybody is well too.
Yeah. After a long time, we could see.
Yes, yeah.
Nice.
Good morning, Professor Mishra.
Good morning.
नमस्ते अखिलेंद्र जी. आपका ऑडियो ऑफ है.
Yeah, good morning everyone. Namaskar Yadav sahab.
Good morning.
Namaste. How are you?
Oh, hello, sir.
Hello, Mohan.
Sir, good morning, sir.
Good morning. Good morning.
Good morning. Sir. Good morning.
Good morning. आपका लेटर तैयार है क्या? Declaration certificate?
Yes, sir. It's finished. Just now, in another 1 hour, we will send this.
Good morning, Dr. Vinod.
Good morning, sir.
How are you?
It's going to 11. Shall we start now, sir?
Wait a minute. Yes, wait a minute.
Yes,
Yeah,
sir.
we can start now. Professor Sopori.
Maybe wait for 1 or 2 minutes more. I think.
Okay. Yeah.
Good morning, sir. Good morning, Professor.
Good morning, everyone. Good morning.
How are you, sir?
All right, all right. Is Professor T.P. Singh joining?
I have no information. Normally, he should be there because
Maybe yes, some.
he has confirmed that he will be joining, but I do not.
In fact, I was not sure.
Yeah, that is what I had alerted Vinod
Right.
that probably you may be in another meeting and.
But I canceled that one, I think.
Okay.
Okay, we can start, I think.
Yeah, very good morning, all of you. We will start the global lecture series. This is the 11th lecture in this series. So I request Professor Sopori to give the welcome address.
Good morning, everybody, and welcome to this global lecture series. I call it 2023 now. It's beginning this series for this year. And what a great privilege that to start with this series in this year, we have person of the eminence of Professor Ganpati Yadav, who will be giving the lecture today, National Science Chair and Professor of Eminence. I think everybody knows him, but he will be formally introduced by Vinod. I'm so happy that he agreed to give this lecture. In fact, I had some other appointment. I had told Ashok that I may not be able to join. But when I heard that Dr. Ganpati is going to give, I excused myself from the other meeting. I thought I must come here and listen to him. It's always a pleasure to meet him and listen to him. Although the area is different, but it's so nice that he covers this in very different perspectives. So welcome, Dr. Yadav, to this global lecture series, and we look forward to hearing you. Back to Vinod for formal introduction.
Thank you, sir. As Professor Sopori told, there is no introduction required for Professor Yadav because most of all the members in this forum knows Professor Yadav very well. But for the benefit of the young student members and other people, let me give an introduction to Professor Ganpati Yadav. Professor Yadav is one of the topmost and highly prolific and accomplished engineering scientists in India. And he is the National Science Chair of Government of India and Emeritus Professor of Eminence at the Institute of Chemical Technology, Mumbai, of which he was Vice Chancellor for over a decade. He is internationally recognized for his seminal contributions to education, research, and innovation in green chemistry and engineering, catalysis, chemical and energy engineering, biotechnology, and nanotechnology. He has published more than 500 original research papers, hold 116 patents, three books with H index of 65 and more than 16,000 citations. He serves as adjunct professor at the University of Saskatchewan, Canada, conjoint professor, University of Newcastle, Australia, distinguished adjunct professor at IIT Guwahati, and distinguished visiting professor, SOA University, Bhubaneswar. He is an independent director on board of 5 public limited companies. Professor Yadav was conferred Padma Shri by the President of India in 2016 and received 2 honorary doctorate. He is also elected fellow of Indian National Science Academy, Indian Academy of Sciences, National Academy of Sciences India, Indian National Academy of Engineering, as well as the World Academy of Science to us. He's a fellow of Royal Society of Chemistry, UK, Institution of Chemical Engineers, UK, Indian Institute of Chemical Engineers, Indian Chemical Society, and is an honorary fellow of Indian Society for Technical Education and honorary fellow of Biotech Research Society, India. So currently, he's a president of Indian Chemical Society and editor-in-chief of Journal of ICS, being published by Elsevier. And he's a president of Maharashtra Academy of Sciences. So with this introduction, now I welcome Professor Yadav for his talk on net zero goal and sustainability, adoption of green hydrogen technology, carbon dioxide refinery, and biomass valorization. Professor Yadav.
Thank you, Professor Vinod. I'm just trying to find out how to start it.
You can share the, yeah.
No, I'm trying to do that. Okay, can you see this? Are you able to see my slides?
No, not yet.
Just 1 minute.
Not yet, sir.
Just 1 minute. I'll call him.
Yeah.
Hello. I'm sorry, that guy who was to do it, he just disappeared, but let me see whether I can do it myself. Just 1 minute.
Professor Yadav.
Just is, I'm calling the person. I can see this is a new system to me. I'm in a different place. I'm not at ICD. Sorry. अरे तुम्ही कुठे गेलात पळून? नाही तुम्ही नाही गेलात. फुल स्क्रीन करा. Okay. Can you see it now?
Yes, sir. Yes, it is visible, sir. Yes.
Yeah, sorry about this hiccup because I'm in a different place. I'm in Somaya College, and so the guy who started, he just disappeared. I'm sorry. So,
Finish.
okay. So the title is already told you. So what I'm going to tell you is very interesting things, which happened over the years. The carbon dioxide concentrations in the atmosphere in January 2020, just before the pandemic, were 410 ppm. Despite the fact there was a low activity during the year, we added 2 ppm of carbon dioxide within a year. And it became 421 ppm May 2022. And today it is almost 423 ppm. And so what is believed that if we don't take care of carbon dioxide, whatever means, we'll have a horrific time. And the temperature of the globe will perhaps go to something like, 2000 ppm in the year 2250. And that will be the end of the world. So this is a prediction, and therefore technological interventions are required. So you all are aware of this Paris Agreement 2015. Some 195 nations have signed this agreement. However, United States did not do that. And so this was one of the pledges by that time candidate, now President Joe Biden, and he said he will commit to this net zero goal. So bringing the temperature of the globe to less than 10 degrees and particularly 1.5 degrees is a very big challenge for the entire world. So therefore, he organized a conference called Leaders Summit on Climate in 2021, and where Prime Minister of India also had participated. Then in the so-called COP26 in Glasgow, India committed to the net zero goal, where it was decided 2050, India said we will do it by 2070. So my question is, why not 2050? Are we not capable of achieving this goal? And so my personal belief is that we can do it. Indian science and technology and industries are capable of doing it, but a lot of policy changes are required, a lot of research and innovation is required. So, and very recently in COP26 in Egypt, there was a disagreement because the entire world was talking about reduction in coal power plants, except oil and natural gas, which the developed world is very freely using. So anyway, that is the story. Interestingly, some of the people, particularly in media and also NGOs, they were opposed to India's program in nuclear energy and coal-based power plants. Remember, the irony is that they were citing the example of Germany. But what happened? After the Russia-Ukraine war, last year in June, the same Germany started power plants using nuclear energy and coal-based power plants. So that is the irony. So it is very easy to give bhashan to the developing world, but not practicing in the road thing. So what it means now, if you look at the historical perspective of carbon dioxide, because that is going to be the biggest challenge, United States during the period 1750 and 2018, when the data were provided by Global Carbon Project, had emitted 397 billion tons of carbon dioxide. India stood at number 7. However, India is number 4 now. If you take European Union together, otherwise India stands at number 3. So what is the prophecy? And this is my prophecy, what is going to happen? That India will be a leading exporter of green energy by 2030. The import will be reduced. Green hydrogen will be less than $1 per kg. And this is where one of the interesting part, which I may talk about, is the so-called 1-1-1 strategy of the Department of Energy of the United States. What are they saying? They say that you must develop technology where the hydrogen cost per kilo will be $1 within a decade. So that means they have given a decade for us to develop hydrogen technologies less than $1. It is also said that it will be India's century. And India will be the third largest economy, something like $30 trillion in next 30 years. That was the statement made by Honorable Piyush Goyal. And if that is the case, and if we achieve the net zero goal by 2050, will the world be a peaceful place? And what happens to the so-called United Nations Sustainability Development Goals? So quite interestingly, why we are having this problem? Because ours is the carbon-based economy. So everybody knows about the fossil fuels and the non-fossil fuels, and these days we talk about biorefineries and things like that. If I put the things in perspective, that is oil and natural gas and coal, we talk about clean coal technologies, directly coal to liquid and coal to gas, or gas to liquid and crude to chemicals. This is what is happening. Even companies like Reliance are talking like C2C, that is crude to chemicals. On the contrary, on the renewable carbon side, you can chemically convert biomass into variety of chemicals, or you do biochemical conversions through fermentation or enzymatic conversion of biomass, and you can convert biomass directly into energy and materials. See, what it means in everywhere is that the energy and environment are intimately connected. More the energy, more environmental damage. And this is where carbon dioxide refinery comes into picture. So since we are dealing with chemicals and society has a lot of apprehensions about chemicals and chemical industry, I put this general slide to make people aware that there is no life without chemicals. And can you show any 3 man-made materials or products without the use of chemicals? The answer is simply no, because whatever you use, it uses chemicals. And if somebody can show 3 of these, he will get a prize of 100 million pounds. This has been waiting since 2008. Nobody has claimed it. And at the most, what is going to happen? The queen on the pound will go and King Charles will come there. That is what is going to happen. And so what it means, we are generating waste, and the waste generation is rising globally. To be honest, right now, our waste generation is something like 1.16 kg per capita per day. So that is not going to be viable solution for us. So can the waste be converted into wealth, and how do we do that? So that is the theme of my lecture. So in the Sustainable Development Goals, the issue is you have goal number 1, which is no poverty and zero hunger, and goal number 9, which is industry, innovation, and infrastructure. So what it means, when we have socially acceptable, environment-friendly, and economic technologies, then only we'll be able to achieve this SDGs. So interestingly, what is being talked about these days, the so-called circular economy and recycle engineering. I'm giving emphasis on recycling engineering because this is where chemical engineering play a very important role. So let us look at the recycle engineering. Whether you do a recycle of material or energy, these processes will be physical, chemical, and biological. And these are all red processes. So if we talk about so-called process intensification, it means we increase the rates, reduce the volume, and reduce the waste. So there is a tremendous scope for Indian chemical and allied industries, and particularly the so-called green hydrogen and green ammonia, which will be used across all disciplines and industry. So waste to wealth, whether it is solid, liquid, and gas, that is the theme. So how I can put my lecture in perspective? See, it has been said that if we do not have the so-called circular economy and only the linear economy, we will need 3 years if we don't recycle, reuse, and reduce waste. And now, since we are talking about the so-called solar energy, wind energy, and all that, so what happens of the used solar panels, wind turbines, plastic batteries, construction, and debris work? So some of these issues I will talk about. Interestingly, so look at the battery recycling market. Battery recycling market, whenever you use any EV, people talk about, and government of India is committed to have EVs by 2030. If the electricity which is generated for that EV is coming from coal-fired, plants, then it is coal-fired EV. It is not electricity EV. This is the flip side of it. And what happens in this battery market, when the battery capacity goes down to 80%, it becomes useless. That means we have to look at the other part of the story, that where we can use this 80%, capacity reduced batteries. Normally we talk about nickel, lead, lithium, okay? And this is where the recyclability of market comes into picture. And right now, China is #1 in this area. Okay, so the recycling for battery environment is whether it is plastic, lead, electrolytes, these are the issues which need to be addressed. And all these issues can be solved by using one of these three processes, that is physical, chemical, and biological. So look at the circular energy storage. China is dominating right now in the recycle and second life battery, almost $45 billion by 2030. And there will be almost 1,000 gigawatt hour of remanufacture and second life batteries. So this is very good, because this is what I call a recycle engineering. So the 75% of electric vehicle batteries, everything from e-scooters to buses to forklifts and trucks, in 10 years' time could be remanufactured into other vehicles. So what it means, there is a tremendous scope for industries in recycle area. And so battery recyclability, because they are highly recyclable and they can be used for so-called repurposing, and therefore, which is important for everybody to find out the battery recyclability for achieving the sustainability goals. And there will be something like 8% CAGR in this. Right now, China is growing at 9% in this particular area. United States is less, about 6%. But India has a tremendous scope in battery recycling. So battery recycling market is about 8.74 billion. That was in 2016, and this is going to be increasing. What happens even in this industry when you are talking about recycling? There is again a problem of carbon dioxide. That means we have to tackle carbon dioxide, and we have to reduce the carbon dioxide emissions in this area also. One of the interesting parts in this is that look at the world energy scenario. In 1995, the share of the renewable energy particularly, was about 18%. And this is going to be 73% by 2050. And in that, what will be very important? That you will have solar, wind, and hydrogen, nuclear. Coal will be still used. And the requirement of energy by 2050 will be 49,000 terawatt hours. So that is the hard fact. So what happens? So since we are talking about biorefineries and all, is it a new concept? Most of the people don't know that. It is not a new concept. During 18th and 19th century, there was something called oileries. And what is these oileries? They used to use whale. So whale's blubber was taken out. From that, they used to make soaps, and at all it was used for illumination. So over a period of time, because of the excessive hunting and collection of whales, the population of whales went down substantially. Almost it came to an extinction. So this is where the birth of this carbon-based industry came into picture. So this is how coal and crude oil saved the population of whale, because they became the providers of energy, chemicals, and materials. And we have to thank Colonel Edwin Drake. He started this oil industry in 1859. He drilled the first well in Turtlesville, in Pennsylvania. And what was happening then? They had to, because it was viscous, they had to crack it. They had to heat it. During heating, accidental cracking. So it became the thermal cracking. In thermal cracking, what happened? Whatever was coming out as gasoline or petrol was useless. So they used to dump it in sea, lakes, and rivers. So only kerosene and other fractions were used. And until the time in 1907, Henry Ford introduced the first automobile which used this gasoline-driven vehicles. And that is how this petroleum so-called petrol or gasoline found uses. Then this industry became highly competitive because everybody was concentrating on carbon. And this is the reason for what we are having the so-called GHG emissions. So in 1920s, there were a lot of evolutions, okay, in the technologies, and the industry grew. Afterwards, instead of the thermal cracking, they started doing the catalytic cracking. So they used clays, So Howdry was the one who used it. And later on, you will find that then we moved all to, so during Second World War, the Allied forces, which included Russia, won the war against Nazi Germany because they had better aviation fuel. And remember, this was all catalytic processes. So the catalysis played a very important role during Second World War. The flip side is this, that in Russia, there was a general called Vladimir Ifatov. And Ifatov was a very good scientist. He developed all these catalytic processes, which you are talking about, platforming, reforming, hydroforming, name it. And so at the age of 60, he retired. And he took a train and he told his wife, we are going to Germany. And he said that he told his wife that for the last time you are seeing Russia. He had no knowledge of English. He went to Germany. EOP was waiting for him there. They hired Ifatov for his scientific contributions. Okay, not only that, another interesting part, but he had also a girlfriend, a concubine. He said that he needs her also. And so they hired her as well, EOP. That's the interesting part of the story. But what happened? Vladimir Ifatov was nominated for Nobel Prize many times. He was not given it simply because he was a military general. So, however, he was later on inducted into the Hall of Fame. That is interesting part of it. So now the refineries are highly complex and every carbon atom is being used for something or other. So yes, we know that. So what is happening? Because we are using carbon as a fuel, carbon dioxide emissions in the atmosphere are increasing. So this is where the role of hydrogen economy comes into picture. So I'm going to tell you a little bit about it. So like in our Hinduism, we say Brahma, Vishnu, Mahesh, the Trinity, or the Christians may call Father, Son, and Holy Spirit. My belief is that the new Trinity is solar energy, wind energy, and hydrogen energy. In this, hydrogen takes the supreme position because hydrogen can be used to convert biomass, including the waste biomass and plastics, into a variety of chemicals and materials by different technology. So one of the things which we ourselves did, for which a lot of things, we have more than 120 patents now, it is so-called ICT OAC technology, the ONGC Energy Center, which is supporting my research in 2006. And this is one of the ways to do it. Quite interestingly, the Ministry of Power last year notified a green hydrogen policy. And so green hydrogen and green ammonia. And what are they saying? That they say that we will meet 50% of the country's energy needs by renewable energy by 2030. So in other words, what will be the feedstock? It will be water and air. Two simple, entities will be the feedstock to achieve this by 2030. So what happens? So it means, what is the meaning of this green ammonia? You take water, you take any renewable energy, whether it is solar, wind, or hydro, and you do water electrolysis, or you can have a thermochemical process. That is what we have developed in ICT. All these processes, both these routes, water electrolysis is being talked by across the country, world, by many industries and governments. And the electrolyzers are very, very expensive. So our technology is a competing technology to water electrolysis. And what we did, I will tell you a little later. So that is green hydrogen. From here, you do pressure swing adsorption, separate nitrogen. And when you have nitrogen and green hydrogen, that becomes green ammonia. And so right now we have infrastructure for ammonia transport. So ammonia can be used for whatever purposes you talk about as far as the energy industry is concerned. So the consumption and production of hydrogen is very, very important for us. So hydrogen production, so we have, the green hydrogen, the blue hydrogen, and the gray hydrogen. So this is what is going to happen by 2050. So about this industry will have a growth rate of about 8%. And I mentioned earlier that 49,000 terawatt hours of energy, of which 24% will come from hydrogen. Okay. What is interesting in this, that since I'm talking about carbon dioxide and we have to reduce carbon dioxide concentrations in the atmosphere, in 2020, the carbon dioxide emissions were 35 gigatons, billion tons. Okay, now last year it became 40 gigatons. And we have to bring down the concentration of carbon dioxide to less than 10 gigatons, then only this set goal of 2 degrees or 1.5 degrees will be achieved. So what it means? So hydrogen is going to do all this transformation. So hydrogen is going to be the real savior. I would not go into the details of the properties of hydrogen, but it is very, very interesting, fuel or energy carrier. So we can have green energy generation, transportation of two-wheeler, in the two-wheeler, three-wheeler, four-wheeler, you can have fuel cell technology, the IC engines, then synthetic fuels from carbon dioxide, upgrading of oil, bio-oil, which is normally produced by pyrolysis of biomass, then hydrogenation of biomass, then green ammonia and fertilizer industry, green metal including steel and nickel. Chemical and allied industry uses very little quantity of hydrogen in comparison with the rest of the industry. And then waste plastic chemical recycling, okay, and of course heat and distributed power. You will find that the energy density of hydrogen is the highest in comparison with normal, fuels like wood, ethanol, coal, LPG, and whatnot. So hydrogen is very good, energy carrier. So what it means that we need to have hydrogen production technology, and they must be cheap. So then only the so-called net carbon zero goal can be achieved. So there are typically 3 hydrogens which normally talk. In fact, you can go on talking about 5 different hydrogens. Green hydrogen is electrolysis water and including this thermochemical behavior. It is a gold standard. Blue hydrogen means steam reforming of any carbon source, typically biomass and biogas, bio-oil, where the carbon dioxide has to be captured and stored and used. So even if you capture about 90% of that carbon, then this becomes blue hydrogen. And gray hydrogen is a steam reforming of fossil fuels, including coal and natural gas or methane, that produces something like 11 tons of carbon dioxide, per ton of hydrogen. So that is gray hydrogen. And something which is come into picture these days is the so-called, pyrolysis of methane, where you get directly hydrogen and carbon. That carbon can be carbon nanotubes or what. So this is called turquoise hydrogen. All right. So what happens? Suppose we have biomass. Since we will not have any crude oil by 2050, by the current means of our current technologies, we have to use biomass as a material and energy source. So water splitting will be very important. Thus, the importance of hydrogenation and oxidation in biomass becomes important. So, in other words, water becomes important. So, one of the examples which we can talk about is the biomass, which is normally the agri-waste which is burned by the farmers. In fact, that is something like 300 million metric tons of that is burned every year in India. And that causes fog, etc., and those who are living in Delhi know about it. So, yes, you are all familiar with the lignocellulosic biomass, whether it is coming from agriculture residues or waste streams, wood, MSW, or whatever. We can convert through gasification to syngas, liquefaction, pyrolysis to bio-oil, and liquid phase reforming, going to xylose, glucose, lignin. And all these chemicals can become feedstock for other industry. So one of the things which we have done in our laboratory is many chemicals we produce from cellulose. Okay, importantly like furfural, 2,5-furan dicarboxylic acid, HMF, and whatnot, or sorbitol. So the sources of biomass could be anything. It could be forestry, it could be agricultural crop, or animal residues, name it. So they can become sources for making so-called biorefining. So in other words, the farmers can benefit by hydrogenation of biomass and convert waste to wealth. So that is one important thing, which they do not know right now. So ultimately what it means, whether you have a carbon coming from fossil fuels or by the biomass, the carbon dioxide has to be converted. So this is where the carbon dioxide refinery concept comes into picture. So what is the carbon dioxide refinery? You can see the carbon dioxide refineries, we can make methanol, urea, hydrocarbons, dimethyl ether, and dimethyl ether is a very good substitute for LPG and diesel, formic acid, organic acids, propylene carbonate, alcohols, and whatnot. Okay, so a lot of chemicals can be made by any of these processes, whether chemical or biological, carbon dioxide, bulk chemicals, and fine chemicals. What is important is that you require a catalytic technology. So one of the things is methanol. So methanol can be produced from carbon dioxide directly. Dimethyl ether can be also produced. So we have developed technology for that. And the government of India, particularly the Niti Aayog, is talking about methanol, economy. So yes, methanol is a versatile feedstock for production of fuels and chemicals, and it should be used only for chemical manufacture, not for fuel. So I will tell you that also. So very interesting thing, the entire world is talking about bioethanol and burning of bioethanol or mixing it with the fuels, for example, petrol or diesel. Should it be done? So we said we took this as a challenge and tried to do some calculations and published it. So for example, if you look at the hydrogen usage in oil refinery, there are 8 different stages where you use hydrogen, and that hydrogen comes from natural gas steam reforming. Okay. At the same time, I mentioned to you that biomass also needs hydrogen and oxygen for valorization. So the processes in refineries are catalytic cracking, hydrocracking, catalytic reforming, HDS, HDN, HDO, and HDM. These are 8 processes which require tremendous quantities of hydrogen. All refineries need that. Why not use green hydrogen instead of using this gray hydrogen? That is the question. So yes, so you can compare the so-called petroleum refinery versus biorefinery, and what biorefinery can do, I need not tell you. What is important is that what is good. Suppose I take 1 kg of crude oil, I get something like 32 megajoule of fuels plus 0.2 kg of chemicals. However, if the biomass is converted only into fuels, this is what we are talking about, it is only 6 megajoule, or we can produce 0.8 kg of chemicals. So we did certain analysis. What happens? This is based on the world capacity at that time of 97.4 million barrels per day in processing by refineries. So if that is the case, the fuel which is produced that time by using that capacity is something like 215 barrels per second. However, if you convert 100% of biomass into only fuel, it is only 10 barrels per second. If we, on the contrary, if we convert this biomass into chemicals, it is 320 barrels per second. That means this becomes, very interesting aspect. Therefore, instead of burning, these biofuels, it is better to convert them into chemicals and materials, and all energy sources should come from non-carbon sources. Then only we'll be able to achieve the so-called net zero goal before 2050. See, carbon neutral is good, but carbon negative is the one that should be the target in all technology. Yes, carbon we should use for only chemicals and materials. So for instance, see bioethanol. Bioethanol can be burned, that, and you get ethylene, but variety of chemicals can be produced from bioethanol. In some of these, fermentations units where they are making ethanol, they are testing this ethylene thing. Right now, I mean, somewhere we were discussing how do we do this. So polyethylene, ethylene oxide, ethylene glycol, styrene, all these chemicals are much more valuable than ethanol being burned as a fuel. So what it means, carbon should not be burnt as a fuel. Carbon should be used for making chemicals and materials. Only then we will be able to achieve the net zero goal before 2050. Bioethanol is more valuable as a feedstock for biorefinery than as a fuel, as our analysis shows. This paper which we wrote, there are more than 9,000 downloads of this. Many people, including, the planners, asked us. So as the renewable energy sources which we should have is solar, wind, geothermal, nuclear, and hydrogen. So for example, here are these structures of seminal hemicellular. Typically, you can see the colored portions of this. These are very valuable sources of different chemicals and materials, whether it is coumaryl alcohol or confenyl alcohol or whatever. So all these processes require hydrogenation, hydrogenolysis, dehydrogenation, oxidation, condensation, name it. And so very interestingly, so C5 and C6 sugars which are found in hemicellulose are precursors to a number of chemicals. So that is one part of the story. And lignin can be converted into a variety of things, whether it is hydrocarbons, we can go to benzene, toluene, xylenes also, phenolics, vanillin, and go to syngas route and make Fischer-Tropsch, and all those chemicals can be made from lignin. So what it means, if you have biomass, you separate this cellulose and hemicellulose part, whether it is acid or alkali or so-called ionic liquids. Remember on the top portion, C566, these are all metal catalyzed oxidation, hydrogenation, hydrogenylation, dehydration. All these valuable chemicals are produced from C5C6 sugars. And from lignin, instead of burning it, we can have diacid, syringaldehyde, vanillin, propylphenol, and whatnot. These are again oxidation, hydrogenolysis, and all these things. So chemical conversion of biomass into chemicals, by catalytic conversion, is a better idea than burning it as a fuel. So one of the things, since I talked about my own process, this is a thermochemical water splitting to producing hydrogen. So we have sulfur iodine cycle and vanadium chlorine cycle and copper chlorine cycle. There are 216 water splitting cycles which are studied and reported. So one of the things which we chose, although we had also worked on sulfur iodine, is the so-called copper chlorine cycle. And this copper chlorine cycle, we can produce hydrogen in less than $1 for a capacity of 100 tons per day. And we are, we proved it in a number of ways. Proof of concept, we got several patents, international patent. The first patent I got was in USA, then Canada, then Germany, UK, Japan, and all that. So this is a very important technological breakthrough. However, we have to have cost of production of something like 100 tons per day. So this copper chlorine cycle is known to people, but we modified it, and therefore we got these patents. And we have a technology level of more than 8 TRL level. And so we have now inquiries coming from variety of users, steel industry, fertilizer industry, including foreign companies. And so what I'm suggesting to you, that once you develop this technology development is a very difficult part of it. So remember, I've been working in this area since 2005. Number of years we have spent in improving upon the technology, because ultimately it has to be net energy positive and the cost of production must go down. So this particular slide shows that what we do. So we take solar energy. We have developed a molten salt, mixture. We have got patented, and then we use copper chlorine cycle. We just put hydrogen, water in that, get hydrogen and oxygen, and all those reactions which I told you before, we can do it. So we have produced methane, we have produced the so-called SNG, so the biomass conversion, so hydrocarbons, methanol, dimethyl ether, formic acid, formates, all sorts of things can be done by using this. All these areas we have patented. So and this is supported by ONGC Energy Center. Therefore, the technique is called ICT OAC process. So look at the cost of hydrogen. Why everybody is working on these electrolyzers? Because they think it is very attractive, but it is very expensive. Right now, it is about $1,100 per kilowatt, and that has to be brought down to something like $220. The cost of this carbon capture and storage increases the cost of steam reforming of natural gas, and that will be anywhere from $990 to $1,850 per kilowatt hour. So low carbon fossil-based fuel cost in 2030 is expected to be $2.5 to $3. Right now it is not, and that is why everybody is talking about green hydrogen. So what we are going to talk about, so for example, I have got all these technologies which are reported. Unfortunately, the last part, which is my own technology, where we are saying that we can produce hydrogen in less than $1. Look at the other places. When you have coal, you get something like 1900 tons of carbon dioxide per ton of hydrogen. Natural gas is 11. If you do pyrolysis, this so-called turquoise method, there is no carbon dioxide. Natural gas, blue hydrogen is 0.2, green hydrogen 0. Last one is the my process. So we compared that and we say that we can produce hydrogen less than $1. So we are in the news and we are getting a lot of inquiries, even big companies. And since we are doing this pilot scale in Goa, we have to wait for at least a year and a half for developing and transforming this technology to industry. Okay, so what is the success? So we have converted carbon dioxide to methane and higher carbon cap. We have got international patents. Our catalyst does not decay even 2000 hours. And we can use any carbon dioxide, including the coal-fired power carbon dioxide. So ONGC Energy Center is supporting it, and we can use it. Like, for example, in Delhi, they use this hydrogenated this compressed natural gas, where they can have about 10% of hydrogen. I'm saying I can make it without that. I can take carbon dioxide and directly convert it into SNG. So that is one part of the story. Another is CO2 to dimethyl ether. Dimethyl ether is an excellent substitute for LPG and diesel. So this is what policies require. So a lot of companies are interested in that because LPG infrastructure can be used. So we have proved that. And so right now I'm in Somaya because Godavari biorefinery is their thing, and we were discussing about the technology transfer to many other industries. So they produce a lot of carbon dioxide in their fermenters, and that can be used for making dimethyl ether. Okay. So the another thing is the carbon dioxide to methanol. Many companies are interested in this. We have got international patents. Again, this has been supported by ONGC, and we are trying to sell this technology. So it can go into green methanol, green urea, and green fertilizer industry. And 14 biomass platform chemicals, including these include, I'm just giving a long list here. These include both chemical and biological catalysis. So here we have valorization of HMF, furfural, dimethyl furan, linoleic acid, glycerol, and all those things. Remember, the glycerol does not become effective, the so-called biodiesel, unless glycerol is converted into something else. And there are something like 24 different high-value chemicals can be made from glycerol. So the other part of the story is the consumer plastics. So I have a different take from what others are saying on this. There are 7 different types of polymers which are used, and these are consumer plastic. So what is happening in all these cases is that, this is the where government is talking about SUP, single-use plastic, and banning it. My take is different. My belief is that nothing should be banned. If one technology creates a problem, another technology should solve it. So in the case of these plastics, what is required is segregation and then technology, chemical recycling, for example. How that can be done? So single-use plastic, many countries are using it. In United States, different states have different laws. Somewhere there is a plastic bag ban, like California, then the plastic taxes are involved, or there is recycle and reuse. So can we encourage recycle and reuse? Because India has banned also from 2nd October 2021. Now, what do we do in this? So for example, ban is not the solution, and I will tell you, if one technology creates a problem, then and this problem is because of irresponsible citizens. Another technology should solve it. So how do we solve this problem? So that is, for example, you have this young boy coming to your doorstep with a newspaper, he drops it. No housewife will throw the newspaper. In fact, the Raddi will get more money than the value of the newspaper, right? That means they sell it. So there is a proper recyclability of this. Can we not do this for plastic? Arguments like, suppose there is a deposit on every plastic article, irrespective of the weight and size, citizens will be encouraged to return. So another boy comes to your home and says that give me the milk pouch or PET bottle, and he refunds your deposit. We can create white collar rag pickers because that will lead to environmental protection, and these material will become very important source of fuels and hydrocarbons and what. But this is what is happening. So let us look at some of these things. So chemical recycling, upcycling, and downcycling of plastic is the only solution to solve the problem, because plastic was introduced as a substitute for paper, because paper used to dilute the forest. So what we can do? So plastic waste recycling, zero order, primary, secondary, tertiary, quaternary. But what is important is that waste plastic, chemical recycling, whether it is thermolysis, chemolysis, pyrolysis, gasification, all these processes can be used for converting plastic into valuable chemicals. So chemolysis, for example, hydrolysis, glycolysis, aminolysis, alcoholysis, and acidolysis. So, and the hydrogenation solves all the problem, because this, it can handle any problem. Mixed plastic, for example, chlorine, nitrogen, oxygen, sulfur, HCl will form, ammonia will be formed, or H2S will be formed, and that is handled by the technologies which are known to the refinery industry. So yes, PVC, PET, polyamides, and rubber, all of these can be hydrogenated. So very interestingly, this does not become waste, but it becomes a source of, additional hydrocarbons, and you can, it can be also a source of sulfur, for example. So waste plastic catalytic technologies, you can see all these plastics can be handled by using chemical recycling. Only issue is that how do you make people to recycle the plastic which they have? Instead, because it is free right now, they throw it. If it was not free and there was a deposit on it, they will definitely return it. So that is the only solution. Not banning is not a solution. Then it leads to all sorts of illicit businesses. Then the authorities make money and whatnot. So it is not a good idea. Ban is not a good idea. So for example, PET waste chemical recycling, we can do a variety of things, whether it is glycolysis, hydrolysis, methanolysis, aminolysis, ammonolysis, name it. We produce a variety of chemicals, including the chemicals by, biocatalysis. Another highly polluting area is steel industry. Okay, steel. India produces a lot of steel. Last year we produced 6 million tons. This year it will be 120 million tons. 2030 will be 300 million tons. But the interesting part is that 1 ton of steel produces 2.38 tons of carbon dioxide. So instead of that, if we use green hydrogen, it becomes a green steel, like green nickel. Okay, so hydrogen is a solution to the steel industry's pollution. So yes, I mentioned to you that whenever you have steel production, carbon dioxide are emitted. And India is number 2, China is number 1 in steel production. So hydrogen production technology, since hydrogen takes a central stage here, we have many technologies available. So we, compare the technological maturity of steam reforming, partial oxidation, biomass gasification, alkaline electrolyzer, and so something like 19 published, technologies, where the feedstock is natural gas, coal or woody biomass, algae, name it. The cost of hydrogen varies anywhere between $1.5 to $10. So we compared our, technology with that, and we found that we can make it at less than $1. So this is where, because it is a technology development, it is not just research in the laboratory, it takes a lot of effort. So we also studied, the materials of construction for handling corrosive systems. So the future cost of this electrolytic hydrogen has to be less than $2. Then only the so-called hydrogen economy will be reality for across the world. So by 2030, most of the world would have shifted towards that. And as I mentioned to you, the so-called 1-1-1 principle of United States government is being aimed at by everybody. So in 2050, we will have requirement of 539 million metric tons. This is the rough estimate. It will vary. Only when, that means in comparison with today's requirement, it is tenfold more. So yes, so the hydrogen economy in 2050, everything, whatever we are not using right now, we are using for steel, ammonia, methanol, refining, all other sectors, including SUVs, cars and whatnot. Everywhere hydrogen will be used, and this is where with the hydrogen technology. Only when the society accepts hydrogen as a carrier, then will it happen. So another problem which people normally ask about is hydrogen safety. How safe is hydrogen? Hydrogen is 14 times lighter than air, and it is safer than petrol and diesel. Now this statement may, alarm you, but that is true. Hydrogen fuel tanks are safer, than the conventional fuels. So this tests have been done in variety of cases, and many segments hydrogen can be directly used for IC engines. So to conclude, each work has to pass through three, that is, ridicule, opposition, and acceptance. That is what Swami Vivekananda said. So I think we can expect hydrogen technology to be a reality. And ultimately, the so-called, bioeconomy, circular economy, biomass economy, green economy, all those things will fall in places when we replace non-renewables with biological resources, cascading of biomass, and minimum of power. So ultimately, can we create a zero-waste society? The answer, yes. We have to reduce, we have to reuse, we have to recycle, we have to recover, and the landfill has to be practically zero. That is what is required for this so-called net zero goal. So ultimately, the green hydrogen will be the savior of the world. Carbon dioxide should not be a liability, but an asset to convert. Waste biomass valorization, sustainability through waste minimization and recycle engineering, circular economy, and hydrogen economy can be elegantly converted to make many chemicals from waste carbon sources, including biomass and C1 process. And government of India should use hydrogen economy. And in fact, the green, very big hydrogen plant was unveiled by the government of 4th of January this year. So ICT OAC hydrogen production technology is very promising, and it is one of that. I'm not saying it is the only one. There are many others. And that is the only way to meet the goals of the Paris Agreement. So finally, I must thank a large number of my students who have been working with me over the years. And because of all these things, I was elected to the US National Academy of Inventors. I'm the only second Indian to be in that league, and National Academy of Engineers, one among 21 Indians. And of course, I became the National Science Chair. So I thank you all for inviting me for this global lecture series. And if you have any questions, I'll be very happy to answer. Thank you very much.
Thank you. Thank you very much, sir. It's a very wonderful and very informative talk. So now we will move to the questions from the audience.
Yeah.
One question I have,
Please.
it's such a wonderful lecture, and it really gives us hope that we don't have to fear increase in CO2, but we can make use of it and convert it into energy. Because as a plant scientist, we always say that you produce certain plants which will absorb more carbon dioxide. CO2 sinks we want to create through engineering and see that it can be then pushed back into the soil. So those kinds of technologies. But what you are saying is something really gives us hope that CO2 is not that much going to be affecting us if we convert it usefully. One of the things which I have, this hydrogen economy, especially when we are talking about using it in the transport and other systems, then simultaneously the technology for developing those kinds of engines and other things will have to be worked out in order to use it efficiently in those kinds of systems like transport you were talking about.
In the case of hydrogen, IC engines can directly use hydrogen as a fuel.
The same engines can
they can be directly used. So big vehicles, trucks, and all those things, you can use hydrogen as a fuel directly. Mm-hmm. Another is the fuel cells. Hydrogen as a fuel to the fuel cells, two-wheeler, three-wheeler, four-wheeler, are using hydrogen to generate electricity, and that electricity goes into the batteries and then you use it. So that is another way of doing it. One of the important problems, I tell you, because the hydrogen compression is about 300 to 700 atmospheres. And to bring it in a liquid stage, it requires minus 253 degrees Celsius. So that is again energy intensive. On the contrary, why they are talking about green ammonia? Because green ammonia can be compressed in 10 atmosphere and in liquid stage is only minus 52 degrees. So that is why, and green ammonia, transport is well established across the world because we have been using ammonia for a number of years now. So that is why people are talking. And when you crack it, you get nitrogen and hydrogen. That hydrogen is green hydrogen. Even interestingly, what is important, ammonia can be directly used wherever hydrogen is used, whether it is, boilers or, fuel cells or the IC engines. Ammonia can be used in IC engines also. So countries like Germany and these Nordic countries, a lot of efforts are being spent on taking hydrogen as a fuel energy carrier and being used across everywhere. So that is one story. Because, and the other cases, can we have, even because this is rather now it is an engineering problem. How do you store it? How the supply for a number of, for other kilometers, maybe 400 kilometers, 500 kilometers, refuel that hydrogen. So the hydrogen infrastructure has to be created. So initially in the 1900s, 1910, 20, we had a problem even in India because, how did you develop those, petrol stations and all? It took time. So even for hydrogen, that is going to happen. But as I mentioned, like dimethyl ether as a fuel. See, that infrastructure is already available. LPG pipeline is already available. So you don't have to spend anything. You don't have to modify the engine also. Everything else is intact. So only tinkering here and there, okay, that is what is required. So this avalanche of this DME or methanol, for example, carbon dioxide to methanol. Methanol can be blended in place of ethanol, which is being targeted nowadays. So methanol equally burns very well. Methanol does not produce any flame. It is invisible flame. And all these race cars, they use methanol as a fuel. Okay, so methanol is a very good substitute. And that is why government of India is talking about methanol economy. And methanol can be a very good feedstock for large number of chemicals which are made industrially, including dimethyl ether, which can also be used for the same industry. So there are solutions, but what is important bottleneck is making it commercially viable, having better catalysts, better reactors and things like that. So a lot of things are. So when I was asked by government, the Ministry of Petroleum, they said, Dr. Yadav, you had a very good idea and very nice things which you have developed. And why they were interested? Because I'm not using electrolysis. Because electrolysis means a lot of electricity, the efficiency is not there. So this thermochemical processes, they said, can you develop in 3 years? So I said, yes. And luckily ONGC is supporting me. So we are building a big pilot plant in Goa and another will build soon in Andhra Pradesh. And like this, I'm giving my lecture from this Somya because they are partnering with me with the dimethyl technology. So we are today just discussing about the scale-up issues of that. So people are interested. Many people are interested, and fertilizer industry is interested, steel industry is interested. I got one of the very big transporters trying to have collaboration with us. So you see, I think there's a lot of scope for this green hydrogen in India. And government, on 4th of January, they announced a very big plan. And everybody wants to have a so-called hydrogen valley. Everything is being talked about. They are talking about some 30 industries near Pune trying to create a hydrogen valley. And DST is asking people to invest in land and all, and even they asked me. But I said, I'm an academic institute. I cannot invest. I need money to do things. So that is what happens. So, but it is very exciting. I must tell you, we are exciting times. And we need not have to worry because technology has always beaten and overcome all problems.
Thank you. Thank you so much for your. One more quick question was, should we stop this kind of work on biofuels?
No. You should make biofuels, but that bioethanol can be used as a feedstock for making chemicals, not as a fuel.
Not as a fuel. That's right.
Because it is carbon neutral. No, what I said, carbon neutral is not the solution. Carbon negative is the solution as far as fuel is concerned. Because we require carbon for making chemicals, materials, and all. Without carbon, we cannot survive. But carbon should not be burnt. That is what our analysis showed. We showed that carbon should not be burnt, but make use of it. Like ethanol, we can, in fact, very interestingly, people are talking of ethanol now, but when we became independent in 1955, all our cars were driven on ethanol in North India. They were ethanol driven cars. Now we are talking of going back into history. Because we got this Union Carbide and no seal and all, and started this cracking and whatnot. Then we went to petrol. Okay, so we forgot about ethanol. So it is a cyclic process. We are coming back to ethanol again.
Thank you so much.
Good morning, Lele. This is Professor Lele, Dr. Yadav. I just have a funny query. Like, when we are saying carbon as fuel, we are getting CO2, which we want to reduce. Now, when we are imagining, or perhaps we'll reach that 20 years down the line, hydrogen, green hydrogen as main fuel, then its hydrogen oxide is water. So will it not also solve a problem? Like, is it possible to recover very good quality water in a steel plant when hydrogen is used as a fuel? I mean, just a question.
It's a very good question, because when it burns, it creates water only. So if you look at the water cycle, you are splitting it and making water again. So many places, for example, we can have very nice electricity generated and the water will be useful. Okay. But we require certain quality water. Okay. So people are now trying to find out up to what quality water we require, what is the quantity of water. That these kind of calculations we were doing this morning, because we want to set up a big plant. What will be the expenditure, per kg of hydrogen or per kg of dimethyl ether or methanol? So yes, there are many interesting technological problems, but the best part is that it cleanly burns into water. Hydrogen burns into water. That is the best part of it. And if you use that hydrogen, you create all sorts of chemicals, right? If you take biomass, in petroleum refinery, what we went on doing functionalization, take benzene, toluene, xylene, butane, whatnot, and go on functionalizing. So it was very easy. In the case of biomass, it is defunctionalization. We have to remove the functional groups so that it can come back to this. So I mentioned in one of my slides, we can go to benzene, toluene, xylene, and whatnot, but it is defunctionalization. So you go to bio oil, then hydrogenate it, severe hydrogenation, 50 atmosphere, 200 degrees, go ahead and ultimately come back to the same thing. Okay. So chemical production from biomass will be a very important area. You use any technology, whether it is biological or chemical or whatever. That is going to be a very important part. But water, that is what one of the slides I said, water and air will be our main feedstock for this. That is the reason I said that.
Sir, I have a question.
Yeah, please.
Yes, sir. So my question is related to methane pyrolysis and biomass pyrolysis.
Yeah.
Sir, like when we do methane pyrolysis or biomass pyrolysis at high temperature, we get syngas, then oil and char. But how do we comment on the quality of char that is produced? If it is activated carbon, graphite, or carbon nanotube, at what temperature?
Very good question. You know what they're talking about, the turquoise hydrogen I talked about. What they are saying that you can do pyrolysis of methane, for instance. You will get hydrogen and carbon, and that carbon form will depend on the type of conditions and catalyst, whatever you use. So whether it is carbon nanotube or whatever. In the case of the other, either like, for example, you do pyrolysis of biomass and you go to bio oil and you get all gases, liquids and all, or hydrothermal liquefaction, for example. The bio oil which you get, it can be burned, but its quality is no good. Therefore, it has to be further hydrogenated. Okay, bio oil is no good unless it is hydrogenated. So your question, then the biochar, for example, the quality of biochar. Now, many places it is being talked, that is, you take biochar mixed with fertilizer, it will, have the absorption capacity, slow release fertilizer you can develop. You can have, other nutrients in that biochar, and it is a very good, soil quality improvement. So this is what is going to happen. But believe me, what quality of biochar it will produce, it will depend on the condition, catalysts in reactors and what you use. And it is a matter of research. And you will find a lot of papers have been published across the world in this particular area. This pyrolysis is a hot area which has been debated for more than 100 years. It is not just today.
Yes, sir. Sir, and if we use a catalyst into the catalytic pyrolysis of biomass and we get a spent catalyst, then what can it be recycled?
Of course, spent catalyst has to be treated because it must be, containing some carbonaceous materials, some polymeric material. It has to be removed. The catalyst life will depend on that, and whether the structure of the catalyst is maintained, the fidelity is maintained. So this again, you see, it's a matter of research, but catalyst can be recycled for a certain number of times. It is well known, it's well known.
Okay, sir. Thank you, sir.
Yeah. Can I go ahead, Professor?
Yeah, please go ahead.
Yeah. Okay. Yeah. Thanks for the opportunity. It was a great lecture. As a chemical engineer, I certainly look up to you in many ways. Just to give a background, like I'm from NIRI, but recently I moved out of NIRI, and then
please come to your question. Please come to your question.
Yeah. So that is the background. So that's the reason I'm asking, saying that point. Okay. So my question is, you said you have a TRL. You have a technology which is roughly around $1 per kg. But did you publish a paper in which it has
very good question. Very good question. We published many patents. Okay. The publication of we have done life cycle analysis also. That is even accepted. We have mentioned this in that. But certain things, industries are very wary of publication because I'm supported by ONGC and they would not give permission to publish. But patents, yes, we are done. And I have written general articles. Like in my lectures, I say this. But if somebody wants to know the exact details, what capacity, what cost and all, I can always discuss that with them. So right now we are doing it. Yes.
Okay, so
yeah.
So you're still claiming that it is $1 per kg?
Oh yeah, I'm claiming. We are not only for different capacities. We have seen, and there's a lot of heat pinching also. I'm telling you, it is a very good engineering problem. And I enjoy it more as an engineer. But with it, developing technology, in the laboratory, we can have wonders. But when you go to the high scale, big scale up is a big issue, even in this case. And it is a capital intensive technology.
Okay. And my second question is regarding your point on hydrogen can be used in transport sector. Yes, I agree with hydrogen can be used in specifically in the heavy duty sectors where electric vehicles have not reached it. But as for the typical four-wheelers or light-duty vehicle is concerned, as per my understanding, working with few DOE lab colleagues, as far as the metrics, whichever I am familiar with, like capital or running cost per kilometer, as far as I understand, is the electric vehicles is kind of in a far advanced stage compared to hydrogen vehicle. But still, there is a push from government, Indian government particularly, to use hydrogen in the light-duty vehicles like cars, vans, and etc. Could you justify why there is a still push for that, except for energy security reasons?
The reason is very simple. Because if hydrogen can be produced at a cheaper cost, direct conversion of hydrogen, as a energy carrier and fuel, okay, whether it is IC engine or fuel cell, that is much cheaper in comparison with the electric vehicle, right? Even in the electric vehicle, you require electricity. What is the source of that electricity? Is it nuclear? Is it coal? Is it natural gas, hydro, geothermal, tidal, wind, solar? All those issues matter. In our country, although we are talking about electricity, even using the power, solar power, it is not less than 5 rupees a unit. You understand? Theoretically, you may say it is 2 rupees or 3 rupees, but actual cost is 5 rupees, not less than 5 rupees. So you have to calculate all those things. Okay, and so and it is clean, no, it burns clean. And so if you have a technology for hydrogen storage, okay, that is very important. Since you are a chemical engineer, you know that a smaller tube weighs less than a bigger tube at the same pressure, correct? You understand that. So you have to use storage where you have the material of construction in such a way that even high pressure can be tolerated. Because when you talk about compression and going to lower temperature, it is again energy. That doesn't come free. So you have to have a net gain in any energy form.
Yeah, thank you.
Any other question from the audience?
May not be a question, but one comment I had, maybe Professor JD Yadav can correct me if I'm wrong. I work in system analysis, and my understanding is that biofuels are sometimes seen as negative emission technology as well, with CCS. Of course, in terms of if it is directly fuel is produced and it is burned, then it is very close to petroleum and less emissions. But with CCS, it is considered as a negative technology, and it is pushed as a policy metric in few countries, as far as I'm familiar. Maybe you can correct me if I'm wrong. That's my opinion on it.
No, listen, very good. See, biofuels, you talk about carbon neutral technologies. When does it become neutral? When the same carbon is being recycled. If you take part of the carbon out by some means, then it will become carbon negative, not until then. You understand? No? That is the simple answer.
Thank you.
Any other question? Okay, Professor Yadav, it's my turn. That not any question on hydrogen economy or methanol economy or DME, etc., or biofuel. I always ask eminent people like you who come to give this lecture that for the benefit of everyone, and in particular the young generation, that how you had your childhood. Did you dream of becoming such a great scientific personality? Did you think of adopting engineering? How did you think of merging material engineering, chemical engineering, biological engineering in your professional life and all that? Would you share with your...
Very good question. This is an excellent question. I was born in a small village where we did not have proper school. We used to study in temples or under tree. We had 7 standards, but 5 teachers. So I studied in that condition without using shoes and what. And I went to a city, but the only thing I had was I was highly disciplined. I never took any failure as negative. Okay. And I was always confident and consistent. Most important part is consistency. You could be highly brainy, you could be Einstein's brain, but the consistency lack, and people give up easily. I never give up easily on anybody or anything. Many of my students used to come and say, sir, you are highly demanding, I want to quit. And I used to tell them, no, nothing is wrong with you. Only thing, you are not living up to your potential. You have much larger potential than what can you. Yes, I was ambitious, but I was never jealous of anybody. I always accepted everybody else, as a role model. And I've been always humble, because you can always get some failure. Nothing worse. Every time, not all ideas work. You know that some ideas don't work, but the side lane is better than the main lane. Sometimes we fail and we divide something else. So even in this hydrogen technology, first 1 year, we never had anything. And ONG used to, in fact, threaten me that they will stop funding. But I used to tell them, no, we are going to achieve it. So you have to remain hopeful. You have to have a lot of patience. You must persevere. And failure is temporary. Success is autocatalytic. So if you are successful and you apply your mind, but I tell you, even in the case of technology development, it is not overnight. You know for yourself also, no sporadic results will come. Okay, if some student comes and says, oh, I got the results, and he hides the failure, then I think he's not a good student. The failure is more interesting to me because then it makes us think, why did we fail? What is the reason? Was our idea wrong or something else we did not understand about that process or the product and whatnot? So I think, yes, that is very, very important. I read a lot of biographies and autobiographies. I read a lot of philosophical literature, but I lead a very disciplined life. I live very disciplined. I don't drink or I don't smoke or anything. I'm a very simple person. And all along, I've been surrounded by very, intelligent students. And I think we, when we take all the credit for successes, awards and all, it is the award given to the students because they have worked for us. Yes, as a guide, as a supervisor, you have to encourage. And believe me, although I was an administrator and very good administrator at that, I never gave up my research. I always continued to do research because people give excuses. Oh, I'm very busy. I did my research before 9 o'clock, 4 to 9, and after 6 o'clock. During daytime, I always did administration, but never. And all my travels, etc., I'm carrying something to write or read. Many of my papers are uploaded sitting at the airport.
Thank you so much. Thank you so much. Of course, every successful researcher has to understand this point or to become successful, that to accept failure and to do failure analysis. Understanding the failure is perhaps the key. Thank you so much for sharing these thoughts with us, Professor Yadav. Over to you, Professor Sopori.
After hearing such a wonderful lecture, it's not much to add, but what I can say that consistency and his simplicity has led him to solve the complex problems of hydrogen production and all that. And it's a wonderful lecture which we just heard from Dr. Yadav. We hope to see him in Trivandrum and listen to him, to his other research work which he has been doing. And so wish you all the best, and I'm sure the government expects a lot more from you.
Yes, indeed.
and we too. I think you have built up hopes on many, and many people look at you as a role model. They get inspiration from you. Even we think, how much work you could do. So many PhDs, so many publications, and so on and so forth. So I think you summed it up rightly. Continuous working, simplicity, and continuity, working all the time. Thank you so much. Wish you all the best.
Thank you so much. Thank you so much. I appreciate for giving me this platform. Thank you.
Over to you, Vinod.
Okay. Thank you, Professor Yadav. It was a very wonderful and encouraging lecture. And also your answers to the questions by Professor Pandey is really motivation to all of us. So very inspirational. So thank you once again on behalf of BRSI and also on behalf of all the members of the participants in this forum. I once again thank you, sir, for your time for your lecture. Thank you very much. I also thank Professor Sopori and Professor Ashok Pandey, all other members who joined in this meeting. Thank you all, and we will meet you again in the next BRSI Global Lecture Series in the month of April. Thank you very much.
Thank you. Bye-bye.
Thank you, everybody, and goodbye. Goodbye.